Welcome AP Electricity and Magnetism students. As I mentioned in the last video, I decided to split the magnetism topic into 3 videos because of its length. So this is the second of the 3 videos. The first was on the concepts of basic magnetism, magnetic field around a long wire, magnetic force. In this video, we're going to be going over the Biot-Savart law, reviewing that. And then in the third magnetism video, review 7C, we will be going over Ampere's law, which is actually probably the most likely concept in magnetism that will be on the AP. This comes up, I would say, on a free response test maybe once every 3 years. So we have to review it, but just know that it's not as important, in my opinion, as knowing Ampere's law. More likely to be on the test, more heavily emphasized. Alright, so that being said, this video will comprise these topics: the concept of the Biot-Savart law, then the Biot-Savart law applied to the curved arc of current, a ring of current, a finite wire segment, and then I'll show you some quick shortcuts for calculations. As you no doubt remember, the Biot-Savart law is very heavy in calculus. Okay, so it's similar to the distributed charge unit with electric field. And so let's go right into it. I'll explain why. In the distributed charge unit, we use kq over r squared for a piece of an object. Okay, so we broke an object into smaller pieces for which we could use the electric field formula for like a proton or electron, kq over r squared. The Biot-Savart law breaks a wire segment into a tiny segment, ds. Okay? Now, this picture represents the concept behind the Biot-Savart law. So if there's current in this wire, the light line, this little portion of that current, that little segment ds, creates magnetic field vectors around it by the right-hand rule. You put your thumb in the direction of the current, and you see that above the wire, the magnetic field comes out of the paper. Below the wire, it'll go into the paper. But the Biot-Savart law says that at a given radius, see this is a circle, at a given radius, the greatest magnetic field is produced perpendicular to that wire segment. And as you go at an angle less than 90 or greater than 90, the magnetic field gets smaller. And then when at this point, which the current is going directly at, there is no magnetic field and there's no magnetic field here, then the magnetic field switches into the paper, again maximum value at 90 degrees. Mathematically, we could express the Biot-Savart law, those concepts. The magnetic field dB caused by that little segment ds is given by mu 0 I, obviously more current, more magnetic field. The length of the wire segment is also causes the magnetic field to increase. And then we have the sine of the angle right at 90 degrees. Sine is 1, so we get the most magnetic field. And then over 4 pi r squared, so further away the magnetic field gets smaller. So I want to do just an example of using this. Sometimes, you know, we're going to now integrate and find the magnetic field caused by a whole bunch of wire segments. That's coming later, but sometimes they ask questions that utilize the Biot-Savart law without any integration. This is an example that very rarely comes up. So they might say a 1 micrometer segment of a wire produces a certain magnetic field 10 centimeters away perpendicular to the wire. So whatever this is, it's dB0. What angle is the dB 1/2 of that? So what angle do we have to go to for the magnetic field to become half of the size it is here? This is one kind of problem that might come up. So what I do is I put in the magnetic field here at this other angle, some arbitrary angle, is 1/2 what it is at 90 degrees. Now, everything is the same. Like this might be 1 amp, right? Because it's the same wire segment. The same 1 micrometer, 1 micrometer. Okay? The same radius away. All the pi's. Everything goes away except for sine theta. And this is 1, so all that's left is 1/2, because all of this divides away. And so that angle is at 30 degrees. Okay, so right here, 30 degrees away, it's 1/2 what it was at 90 degrees. Another possibility is they might say a 1 micrometer wire, a segment of a wire, certain amperage, like 2 amps, 10 centimeters away. What's the magnetic field caused by, say, 30 degrees away? Then you would plug in mu0, which is known, the 2 amps, the 1 micrometer, 1 times 10 to the minus 6, 30 degrees, 0.1 meters, and you would calculate and directly figure out what the magnetic field is caused by that one little segment of wire. Like I said, rarely comes up. Maybe I shouldn't have mentioned it because, again, in these review videos, we're focusing on what's most likely to come up. Let's move on to something more likely to come up. The magnetic field caused by a curved arc. So what I mean by that is a portion of a circle, right? So this is a circle, and I cut away just a piece of that, and there's a current flowing in that, a certain current. The arc has a certain radius r, and it has a certain angle that it goes through, 2 pi over 3, that's 120 degrees. So that's how far it goes. So it's basically like a third of a circle. All right, so what we do is, the way the mechanics of the Biot-Savart law works, just like in distributed charge, we imagine a little segment of this wire, length ds, all the way over here. It creates a certain magnetic field dB by the right-hand rule. We see thumb in the direction of current, magnetic field comes out of the paper, so dB is out of the paper. If the current went the other way, this way, then the magnetic field would be into the paper, but it's out of the paper. The length of that arrow is given by the Biot-Savart law. Okay? Now, we need to now apply it to this problem. So the whole magnetic field caused by the entire wire will be the sum of each dB caused by each ds. And of course, the sum, an infinitesimal sum in calculus, in math, is an integration. So we're adding up, we're integrating. Let's hold off on the limits. So the Biot-Savart law, I basically rewrite it. The only change is I put capital R in for little r, because that's the size of how far away ds is from that point in question. Also, what's the angle we plug into the Biot-Savart law? Well, it's the angle between the current and the radius, which we can see here is current, radius, 90 degrees. That goes in there. So now we look back and we say, well, what are we integrating with respect to? All of these are constants, mu0 and r and pi, of course, and the 4. So the only variable is ds. So we're just integrating the arc length. And what does the arc length go from? It goes from here, from 0 length to the arc length over here. Now, how did I get this? Now, as you know, the formula for this arc length around a circle, or the circumference, is 2 pi r. This is basically theta times r. The length around an entire circle is the angle times around the entire circle times the radius. But if you're only going a lesser angle than 2 pi r, well, then you plug in whatever angle is here instead for the arc length, which is 2 pi over 3, not 2 pi. So that's the arc length, what it goes through. Okay? So this is the most trivial integral you could come across. ds or dx or dr, whatever it is that integrates to just the variable s. Limit 0 to 2 pi r over 3. We bring the constants, we plug in the limits, 0 in there, and then we get to here, the magnetic field. Now, a couple things I want to point out. One thing I forgot to mention, I should have mentioned earlier, is that very often we multiply this by a trig function when the arrows don't line up. This is going to come later, but every dB caused by every ds is pointing straight out of the paper. So, by the right-hand rule. So we don't have to multiply by any component here, or any trig function to find any component. All the dBs line up. That's why we just skipped right to integrating. The other thing I want to point out is we could redo this for an entire circle and find the magnetic field at the center of a circle. Just plugging in a limit of 2 pi r instead of 2 pi over 3 times r. And that we would find is mu 0 I over 2r for the complete ring. I want to point out that this might come up on a multiple choice. What makes a bigger magnetic field? A small ring or a big ring? And a lot of people would say, oh, the big ring. You know why? Because there's more current, more wire here, and produce more magnetic field. It's actually not true. If you look at this formula, r is in the denominator. Same here too. So the smaller the the smaller the radius of an arc, the bigger the magnetic field at the center. This has more magnetic field, larger magnetic field at the center than this one. So that might be just a quick multiple choice question. Something might be worthwhile to remember. Now again, once again, I highlight the most important step. As you're reviewing this, don't pay attention so much to this because these will change depending on what, the size of the arc. Know how to set this up. This is the key. The rest is detail. Also, as you know, in the AP, it gives partial credit. And so this may be, setting this up, maybe 2 out of 3 of the points, or maybe 3 out of the 4 points of the whole problem right here. So this gets you the most credit anyways. That's what you want to study. That's what you want to, and not worry so much about the details. All right, next setup. We had the curved arc. Now we go to the ring. Okay. So that should be right about there. All right. The ring of current. So what I have is an entire ring, and I want to find the magnetic field along the axis that passes through the center of the ring, some distance x from the center of the ring. So here's the ring kind of drawn in 3D. This is coming out of the paper. This is going into the paper. This is these parts of the ring that are poking through the paper. The current's coming out of the paper here and going around and into the paper there. So the ring has got a radius r, a current I, and we want to find the magnetic field at a distance x along the x-axis. So the first thing we have to realize, if we apply the Biot-Savart law with our right-hand rule, is that the magnetic field goes around this point coming out of the paper. It goes in the counterclockwise direction. So here's the radius little r in the Biot-Savart law. The magnetic field is going to be perpendicular to that, either this way or that way. If it were into the paper, it would go this way. But by the right-hand rule, we see that it comes that way. Okay, so there's dB. Okay, then we realize that as we're going to ultimately integrate around, we're eventually going to get to this point, and this will create a dB. By the right-hand rule, it'll create a dB like this, canceling the vertical component, the y component. The only component that survives the integration is the x component. And so if I label this theta 2, that x component of dB will be dB, since this is the opposite side, I'm going to multiply by sine theta. But this is theta 2, because theta in the Biot-Savart law is over here, which is 90 degrees. I'll explain that. Well, maybe I'll explain that now. Why is that 90 degrees? The current's coming right out of the paper like this. Okay, so straight at the camera, and the radius vector is running along the paper, so those are 90 degrees to each other. All right, so coming out of the paper and along the paper 90 degrees, that's the theta in the Biot-Savart law. This is the theta for the component to select this horizontal component. So dB from the Biot-Savart law times sine of this angle here will give me this component, which is the only one that survives integration. So the next thing, the net B, will be the integral, the addition of all the dBs going around this ring. I'll skip the limits for a little bit, but let me fill in the dB. Remember, we have mu 0 I ds sine theta between the radius and the current, which is coming out of the paper. That's 90 degrees, as I mentioned. 4 pi r squared. The r is not here. The r is the distance from the current to the point where it's creating magnetic field. That's along here, which is a hypotenuse of this triangle. So little r squared is capital R squared plus x squared right there. Okay? The sine of this angle, I could figure that out eliminating the theta variable by realizing that this theta is the same as this theta. Okay? Basically, this is a complement, and then those two are complements, so those two are equal. So the sine of this angle, I'm going to use this triangle again to figure out the sine of this angle. The sine of this angle will be the opposite, which is capital R, opposite over hypotenuse, which is the square root of that squared plus that squared. So there's sine dB and sine theta. Okay? This is the highlighted step because this is the important step. If you just set this up, you'll probably get most of the credit on the problem, at least half. Okay? So this is what you want to concentrate on in your studies. Now if you look, we're going to be integrating around this ring. Okay? So what you should do as you inspect this is think about how the variables change, if they change as you're integrating around. First of all, the current doesn't, mu0 doesn't, pi doesn't. Does x change? No. As I'm integrating around this ring, I'm always the same distance, x here, above the center of the ring. Does r change? That's the radius of the ring. So that doesn't change. R, x, r. None of these variables change. So we're only integrating with respect to s. And that tells us the limits. The arc length around the entire ring is just the circumference, 0 to the circumference, 2 pi r. So this may look like we're setting up for a very complicated integral. It turns out to be the easiest integral of all. We just gather up all the constants in the front here, and then the ds integrates to s from 0 to 2 pi r. Plug in the limits, and then we've got our answer. I forgot to do it on the last, for the arc of current. But as I said in Gauss's law, and I'll say it in magnetism too, when you're deriving these formulas, it's best to, or a good idea, to always compare it to the basic formula for magnetic field around an infinite wire, and do what I call a unit analysis to make sure you didn't make any mistakes. Oops, mu0. So in the magnetic field formula, you always need a mu0. You need amps in the top for I. This doesn't have units. So we need mu0 amps over meters. So we look here, we've got our mu0, we've got our amps. Then we've got meters squared. And then down here, all of this squared to the 3/2 power gives us meters cubed. And if you look at that, that does simplify to mu0 amps over meters. That is a useful check, as I said, even during Gauss's law, checking electric field formulas. For example, if I messed up and somehow I lost that squared, this check would catch that error. And I could go back and look and say, oh, geez, the units are mu0 amps over meters squared. That's the wrong thing, right? And then I go back and I say, oh, okay, I lost the R like somewhere over here. I lost this R or something. I might find that. It won't uncover a missing 2, for example, but it will cover powers in the formula, errors in the powers of the formula. Again, don't focus on this. Study this right here and understand the setup and the thinking and the concepts of that. Okay? Okay, moving on. So far the integrals have been pretty easy. ds integrating to s. ds integrating to s. Not so with the finite wire segment. This is the one thing that's hard all around, the setup and the integral. Okay, the one here. All right, so we've got a wire segment length L. Current I in that wire segment. Oh, I forgot to put I here, so I is going that way. And we're a certain distance d away from that wire segment. So if the wire were infinite or very long, we could use mu0 I 2 pi r, right? But it's not, it's finite. We have to use the Biot-Savart law to figure out the magnetic field. So what we do is we imagine a little ds. Well, instead of ds, we're going to use dx because we have an x-axis here and we're not integrating around an arc length this time. Okay, we're integrating around on an x-axis. The wire being length L, if the middle of the wire is x equals 0, then this is positive L over 2 and this is negative L over 2 from x equals 0. So that's the coordinates of the extent of the wire. So again, we picked a little ds here, and that makes a dB by the right hand rule coming out of the paper up here. The magnitude of that dB is given by the Biot-Savart law. Okay. However, when we integrate, we don't have to pick a component here, like over here, where we had to get the horizontal. Here, all the dBs create a magnetic field that comes straight out of the paper, so we don't need to multiply by another trig function as we did here. So just the Biot-Savart law integrated out. So we plug in, fill in the pieces. Again, we switch the ds to a dx. And then the r is how far away this current element is from the point we're looking for the magnetic field at. That is, well, maybe I'll go like this, the hypotenuse of this triangle, little r, okay? So that will be x squared plus d squared is r squared. Next, we got to, okay, and then, so that's mu 0 I dx 4 pi r squared. We got all that. Now, the sine theta, it's the sine of this angle. So sine theta is opposite over hypotenuse. So I highlighted here to show this is the expression. Oh, the squared looks a little light. Let me fix that. Okay, so opposite over hypotenuse. Opposite is d, that's in the top. Opposite over hypotenuse is x squared plus d squared square root. There, that's opposite over hypotenuse. That's the sine of the angle there. Now, we look and we say we're integrating with respect to x, so we think about what the limits are. I already did that. I figured out that x is from negative L over 2 to positive L over 2 will integrate over that bar, adding up all the pieces of dB from all the pieces of dx at that point. So there are my limits. So this is the highlighted step. Again, study this. Even if you don't remember this integral, you'll still get most of the credit just by setting that up. Understand that. That's the heart of the physics right there. All right, what I'm going to do is just gather up like terms. So for example, I'm going to put all the constants in the front. Mu 0 I d, those are constants in the 4 pi. What's left is the dx in the top, and then these two denominators, this is like 2 over 2 and 1 over 2 combined to 3 over 2. This is that integral. Remember I said you cannot do it with a u substitution. Well, remember I showed you in class with the u substitution, it was like 2 pages. So technically you can do it with a u substitution, but it's just best to memorize. This integrates to x in the top, d squared in the bottom, and then the parenthesis term comes to the 1/2 power. Again, if you don't remember it, don't worry about it. It's not the end of the world. Most of the credit will be right there. So don't shy away from this. Learn this part. Limits. All right, now we plug everything in. X plugged in positive L over 2 here. And then the x squared becomes L squared over L over 2 squared becomes this. And then we got the d squared. And then the same thing here. Negative L over 2 squared is still positive L squared over 4. And then these two become plus. Everything simplifies to that. Okay? Again, don't get wrapped up on these details today. When it comes to the AP, this comes up. You get here, you'll probably be able to, if you can get here, you'll be able to do the rest. And even if you don't, it's not a big deal. All right, unit check. Mu 0, we got that. We've got amps, and we've got meters in the top. D is in meters, okay? All of this meters squared to the 1/2 is another meter unit. So we can cancel these out, and we've got mu 0 amps over meters. The form of the formula looks good. Okay? One last thing for the Biot-Savart law. You know, these calculations can be lengthy and tedious. Sometimes you could see little patterns and shortcuts, and sometimes problems are designed for you to solve them with the shortcuts. Otherwise, it'd take you an hour to solve the problem. What I have here is a wire segment that's long, so it's coming like from infinity, can be considered coming from infinity. Then it curves around like this, and then it goes this way to infinity. Then the current's going that way. The wires are 2D apart, and I want to find the magnetic field at point P. Well, I didn't label point P because I didn't want it to get cluttered. If there were P there, it'd start looking very confusing. So I try to color coordinate to show you the logic behind this. This is kind of like an infinite wire, but it creates magnetic field going by the right-hand rule. Thumb in the direction of the current, magnetic field above the wire going in, below the wire, out of the paper. So there's the magnetic field caused by this wire segment. This has magnetic field by the right-hand rule. As the current's coming around here, you see that at the center of the ring of this arc, the magnetic field's coming also out of the paper. And then this has current, current's coming around, has magnetic field above it coming out of the paper also. So the three segments all produce magnetic field out of the paper. So the net magnetic field will be the sum of all those pieces, added without any subtraction. None of them go into the paper. No need for sine, cosine, or Pythagorean theorem. They're all straight out of the paper. So, what I could do is I know that if this wire were infinite, the correct formula for the magnetic field would be mu 0 I over 2 pi r, d instead of r. But since it's infinite on only one side, it's a reasonable thing to conclude that if you take this half of the wire away and the wire ends here, we have half the formula for an infinitely long wire. And the same for this segment. If it were infinite going like this, the magnetic field would be mu 0 I over 2 pi r. But if we take this part away, it's half of that. Now you could use the Biot-Savart law and integrate from infinity in. Okay, you could do that if you want, but you could also do this just using common sense and reason. And then this, well, if you don't remember, you'd have to do the Biot-Savart law for your limits 0 to pi r instead of 2 pi r. Okay? But if you remember, the magnetic field caused by an entire ring of current, mu 0 I over 2 pi r, then you can take half of that because we only have half of a ring. And then you can find a common denominator, simplify, and maybe get one formula here. But again, I'm not going to do it because I just wanted to point out some of these little tricks. Take the infinite, divide it by 2, that's the half infinite wire, and same here. And then take the ring, divide it by 2, and then that's the part of this ring, add them all up. So that is the Biot-Savart law review. Again, I just want to review what we looked at today. We learned the concept of the Biot-Savart law, this equation. Make sure you know it and how it works. A little concept example here, again, not so important. But the three applications, the curved arc, okay, know how to set up the integral using Biot-Savart law, how to make the limits, what you're integrating with respect to. The details not so important, but learn this for the curved arc. The ring, okay, a whole ring. Well, if you want to find the magnetic field at the center, it would be this, okay, at x equals 0 from 0 to 2 pi r. But if you want to find it along the axis away from the center of the ring, then you've got to do this treatment. Again, this is the key setup step that you know it's the dB times the appropriate trig function to pick the proper component, and then that we're just integrating with respect to S. Okay, so that's the key step. The finite wire segment, okay, again, the big idea is right here, the setup of the Biot-Savart law. Okay, know this step right here. And finally, just, a quick little thing about some shortcuts. So that's the Biot-Savart law review video. And I will see you in the next video on Ampere's law.